For this chapter, we're primarily going to focus on working on different ways to deal with solution concentrations and how we can do calculations with those, as well as a little work with coligative properties. So we're going to start with this question related to using percent by mass. So if a solution is 1.5% calcium phosphate by mass, how many moles of calcium phosphate are there in 27.5 milliliters of solution if it has a density of 1.02 grams per milliliter? To start with this problem, I'm going to convert my volume into mass. The reason I want to do this is we are working with a percent by mass problem, so we need to know both the solute, we need to know things about the solute or things about the solution in grams rather than in milliliters or moles or something like that, because percent by mass uses that. So, let's make that. There we go. Okay. Pen, go. No. My pen is not being a pen. There we go. We have a pen now. So, we want to start by taking 27.5 milliliters. We're going to convert this to liters. To grams, sorry. 1 milliliter is 1.02 grams. I did this with my density. We multiply that out. We get 28.05 grams is how much solution we have. We then have our equation for percent by mass. So first I'm going to write it out with the names. Mass solute over mass solution. Then we're going to multiply that times 100%, and that is going to be equal to our percent by mass. So now let's plug in some numbers. We don't know the mass of the solute. That's what the problem asks us, right? It says how many moles of calcium phosphate. So you should know that that is the solute based on the wording of the problem. We then have mass of solution, which we figured out at the beginning is 28.05 grams. We then have times 100% is equal to 1.5%. So I'm going to divide both sides by 100 and multiply by 28.05. When I do that, my percentages will cancel since I have percent divided by percent. And then I'll be left with grams when I multiply this out. And I'll get that the mass of solute should be equal to 0.421 grams. Now the problem asks us how many moles of calcium phosphate. So I have to finish the problem by converting this to molar mass, or to moles, using the molar mass. And so the molar mass is 310.18 grams. Is 1 mole. So when I do that, I'm going to get that I have 1.36 times 10 to the minus 3 moles. With a note that because I said 1.5%, that actually has two significant figures, I'm going to round that to 1.4 times 10 to the minus 3 moles. That is going to be my answer. So that's how we can do a percent by mass question. So let's look at another calculation. Not that far. So this is the second problem to review problems, and the question was just what is the osmotic pressure of a 1.5 molar solution of NaCl at 25 degrees Celsius? So our equation for osmotic pressure is equal to I, don't forget that part, MRT. So for this one, we're given the molarity, that's right here, and then we have close to the temperature, we just have to add 273. So 273 plus 25 is equal to 298 Kelvin. And then R is a constant. And then we know, where did my pen go? My pen disappeared again. Come back. There we go. So we know that I is equal to 2. This is because NaCl, when we have it in water, breaks apart into Na plus Cl minus. Note that if you had a table of experimental Van Hoff factors, it's not actually quite 2, it's below 2. But if you're not given a table, you're expected to just use the number of ions something that's ionic breaks apart into. And remember, if it doesn't break apart, that I is just equal to 1, and then the equation is just MRT. So now we can plug these things in. Our osmotic pressure is equal to 2 times our molarity, which is going to be 1.50 moles per liter. And then because we want a pressure, and we've got like moles and liters in Kelvin, we can use this R, 0.0821 liters times atmospheres per mole Kelvin. And then we multiply that times our temperature of 298 Kelvin. You'll notice the Kelvins cancel, the moles and liters cancel these liters and moles, and we're left with atmospheres. So when we plug all those numbers in, we're going to get that our osmotic pressure is equal to 73.4 atmospheres. You will notice that both of these equations, and a lot of the stuff in Chapter 13, they're only going to be one step. There's not as much manipulating as there was with the Clausius-Clapeyron, but it's just about using a lot of different equations and being able to identify which to use, which is the main focus. So because of that, I want to look at a third one. We're going to look at a molality question. So how many grams of potassium bromide should be added to 125 grams of water to produce a 1 molal solution of potassium bromide? Remember that molal is a way of saying moles per kilogram. So for this question, we know that we need to solve, move that around, our moles of solute over kilograms solvent is going to be equal to our molality. So we're going to plug our numbers in, and I'm going to plug in our molality first, which is 1.00, and that's moles per kilogram. And on the other side, we don't know moles solute. We're going to solve for that. But our kilograms of solvent is going to be 0.125 kilograms. So to do that, I get moles solute is going to be equal to, oh, right, 0.125 times 1 is 0.125 moles, because the kilograms cancel. Now, we want to convert this rest how many grams? So, we have 0.125 moles, and since we have potassium bromide, that's KBr. And then we need to use our molar mass. Let me see, where's my periodic table? Okay, so when we add those together and get our molar mass, we're going to get this as a molar mass of 114.26 grams per 1 mole. When we multiply those out, we're going to get 14.8 grams of potassium bromide. And so this is how much we need to add. Again, it was a somewhat simple equation, but you'll notice I didn't use, while I'm doing some dimensional analysis inside this, we end up using equations a fair bit more often with these. Note that if you can do it purely with dimensional analysis, that's okay. I just find that's harder to keep track of with some of these equations. But if you want to do it, go for it. So finally, let's look at one more question, and this is a Raoult's question, Raoult's law. So what is the vapor pressure of a diethyl ether solution that contains 54.5 grams of octane and 225 milliliters of diethyl ether at 20 degrees Celsius? The vapor pressure of diethyl ether at 20 degrees Celsius is 379.6 torr, and the density of the solution is 0.713 grams per milliliter. So from this, we're going to be able to figure out what the vapor pressure for our solution is that's got something dissolved in it, in this case octane. So to start, we know that we have P solution is equal to mole fraction of our solvent times the pressure that we have for just the solvent. And so we're actually given the pressure of the solvent, right? We have this here, 379.6 torr. So since we want mole fraction is the thing we need to get because we want pressure of solution. So to find the mole fraction, we need to know how many moles we have of each thing. So we're going to start with our 225 milliliters, which we're then going to do some conversions with. We're going to use the fact that, let's see. So that's our volume. So we've got 225 milliliters. We know that every 1 milliliter is going to have a mass of 0.713 grams. And then if we find the molar mass of our diethyl ether, we're going to get the molar mass is 74.14 grams per 1 mole. And if we do that, we're going to get that we have 2.16 moles of our diethyl ether. We can then do a similar conversion with the mass of octane that's dissolved. That's 54.5 grams of C8H18. When we convert that over, we're going to find it has a molar mass of 114.26 grams is 1 mole. We divide those two by each other. The grams cancel. We're left with moles. And we have 0.477 moles. So now I need to know mole fraction of the solvent. And that's simply going to be equal to the moles of solvent, which is 2.16 moles, divided by the total moles, which is just these added together since there's only 2 components, and that's 2.64 moles. So from there, that's going to be equal to 0.818. So our pressure of our solution is going to be equal to 0.818, because that's our mole fraction. Remember, no units on mole fraction. We're going to multiply it by the total pressure, or the pressure of the solvent when it's pure, which in this case is 379.6 torr. We multiply these together, and I'm going to get 311 torr. It's going to be the vapor pressure of my solution. So hopefully with those 4 questions, it helps out some. Obviously, there are more equations for you to work on, but in general, you see it's about identifying which equation you need to work with. You've got that long list within the chapter, as well as a few additional ones on top of that. But each one, the manipulations are just a couple of steps for each of them. I think the biggest focus on this chapter is being able to do these somewhat quickly and being able to identify especially quickly. That way you're not wasting time trying to figure out just what equation you're using at all.